Alright, so recall that if the vector W is a vector in a vector space V, then W is said to be a linear combination of the vectors V1 up until VR. If in V, if W can be expressed in this form, so W is a sum of scalar multiples of the vectors in V, then we say W is a linear combination of vectors of V1 up until VR. And remember, these are scalars. All right, so, and these scalars are called the coefficients of the linear combination. So that brings us to this example here. If we're given two vectors W1 and W2, the question is, can W be expressed as a linear combination of W1 and W2? That's the question there. Can we express it as a linear combination? Right. So so the question now is this can we express W1 as a linear? Can we express W as a linear combination between W1 and W2? So to establish this is we need to find all right, so let's assume it can be done and see if we can actually do this. So let K1 and K2 be scalars such that we can express W, which is -1, 3, and 2. We can express that as scalar multiples of the vectors W1 plus W2. Okay, so that needs to be K1 -1, 2, 1 plus K2. K2 is 2 minus 1 minus 2. So for that to hold, we need three equations. -1 must be equal to minus K1 plus 2K2. That's the first equation. Okay, that's one. The second one needs to be 3 needs to be equal to 2K1 minus K2. That's the second equation. And the last one is 2 must be equal to K1 minus 2K2. Alright, so now continuing, we can say then that what we're going to do is we can take 2 and add twice 1, 2 plus twice 2 plus 2 times 1. That is going to give us that's going to give us minus 2K1 plus 4K2, and you're going to add that to 3 equals 2K1 minus K2, and from that we have that 1 is equal to 3K2, and from that we have the K2 is a third. Okay. Okay, hence we can solve then from 1 we can then get that minus 1 is equal to minus K1 plus 2/3. Okay, because K2 is a third, and that's going to imply that K1 is 5 over 3. Okay, carrying on, we get that from 3. We get that therefore 2 has to be equal to K1 if the system is satisfied, which is 5 over 3 minus K2, which is 2/3. All right, now 5 minus 2 is 3 over 3, which is equal to 1. Now can 1 be equal to 2? Can 1 be equal to 2? No, 1 cannot be equal to 2. So so it follows that W. All right, so it follows that W is not. It's not a linear combination. You cannot solve it. It's not a linear combination. It's not a linear combination of the vectors W1 and W2, because we cannot express W as the sum of scalar multiples of W1 and W2. I cannot find scalars K1 and K2. The system I'm trying to solve has no solution. Alright, so next we are asked to show whether this vector is a scalar multiple of those three, is a linear combination of those three vectors. Now it's important to note that the space we're working in here is Pn, which is the set of all polynomials of degree less than or equal to n. Okay, so sometimes these problems can be done quickly by inspection. So if we are to look at B, note the following. All right, so we can note that so you can take if you look at minus P1 and you add that to P2, and then you add that to P3, you get basically -1 plus the second polynomial, which is 1 plus x minus x squared, plus the third polynomial, and then you can clearly see that that is going to add up to 1 plus x plus x squared. And this is a what's this polynomial? This is polynomial p. Alright, so hence the vector p is a linear combination. It's a linear combination. It's a linear combination of the vectors P1, P2, and P3. All right. Okay, Theorem 3 states that if S is a set of vectors, and it's a non-empty set of a vector space V, then we have both the following. The set W of all linear combinations of vectors in S is a subspace of V. Alright, so the set of all linear combinations of vectors in S is a subspace of V. Then also the set W of all linear combinations of the vectors in S, it's the smallest subspace of V that contains the vectors of S, in the sense that any subspace that contains S the vectors of S must also contain the subspace W. Okay, so let's go and see why this is the case. Let's go and see why this is the case. Okay, so let's take two vectors U and V out of W. And now we're going to show that in fact the set W of all linear combinations is of all linear combinations of vectors in S is a subspace of V. That's what we're going to show. All right, then we can express U as a linear combination of vectors in S because we let U be in W, and W is the set of all linear combinations of vectors in S. So that's how we can express U for scalars A1, A2 up until AR, and we can also express V. We can express V as a linear combination of the vectors in S. So we can find scalars B1 up until BR such that V is the sum of these scalar multiples. Okay. So now we need to look at the sum of these the two vectors U and. Okay, so there I've got my vector U and V, and both U and V are in W, so they're linear combinations of vectors in S. So now what I'm going to do is to show W as a subspace, I need to show W is closed under vector addition and scalar multiplication. So now if you look at that there, if you look at the sum, if you look at the sum of U and V, you can see that you can gather your like terms, and you can easily see that that is a linear combination of the vectors in S, so therefore it has to be in W. Okay, if you look at the scalar multiple of the vector U, then it is clear that that's a linear combination of the vectors in S, because it can be represented as a sum of scalar multiples of vectors in S. So that's also in W. So we can clearly see that W is a subspace of V. Okay, so next we need to show that the set W of all linear combinations of vectors in S, it's the smallest subspace of V that contains the vectors of S. So what this means is if you take any subspace that contains the vectors of S, then that subspace must contain W also. So W is the smallest subspace that contains all vectors of S. Right, so what we're going to do is, so let's take T to be a subspace of V, and this T contains the vectors of S. So now we are claiming that W is contained in T. So let's take a vector U again in W. Remember, W is the set of linear combinations of vectors in S. So we can express U as that given sum there. Now for me to show that this holds, I need to take a point in W and I need to show that it's also in T. Now remember we said T is, so as T is a subspace of V that contains S, so T contains all vectors in S. So we have, what do we have? we have that because S contains all the vectors, because T contains all the vectors in S, and because it contains all the vectors in S, it means it contains all the scalar multiples of vectors in S. So it is going to contain, it's going to contain this vector here. It's going to contain this vector. Sorry, let me just it's going to be that. That is going to be contained in T, and then in general, AR, WR is going to be contained in T. Okay, so that implies that AI, WI is going to be in T for all I between 1 and R. Now remember, T is a subspace, so T is closed under addition. So therefore A1 W1 plus A2 W2 plus everything that you're adding together, ARWR, that is going to be in T, because T is a subspace. So that's going to imply, what is this, what is that whole thing equal to? It's basically equal to U, right? So therefore, U is clearly within T. And that implies that W is contained in T. So any subspace that contains the vectors of S is definitely going to contain a W as well. Alright, so next we have a concept known as the span of a set. So if you have S, a non-empty set of a vector space V, then the subspace consisting of all finite linear combinations of vectors in S is called the span of S. So the span of S, span of those vectors W1 up until WR, remember we said previously the set of all linear combinations of vectors in S is a subspace of V. So span of the set S is just all the linear combinations. That's the set of all the linear combinations. And we showed that that's a vector space. So the span of S is just all linear combinations of the vectors in S. And the vectors in S in this case are W1, W2 up until WR. And remember, these K's are scalars, they're real numbers. Now, if the span of S, if the span of S spans the whole of the vector space V, then we say that W1 up until WR is the spanning set of V. Right, so if we go on to the following example, here they ask us, find spanning sets of the following vector spaces. So there's my first vector space. What would be a spanning set of the vector space Rn? All right, so a spanning set there, we call it S. The spanning set there would be the following set. It would be the set of these vectors here, right? Okay, that's my first vector, and then I just let the one move component, and I let it go through all the components. Okay, so there we have the second vector, my spanning set, and then we carry on right until I have my last standard unit vector, which is I've got a 1 in the last component. All right, so that would be a spanning set. Now, why is that a spanning set? Because if you take, we can just go and investigate this separately. if you go and look at if you go and look at a vector in Rn, so if V is an Rn, V has this form, okay, so it's V1, V2, up until Vn, okay, and that you can write as it as V1 multiplied by the standard this first standard unit vector, plus the second component you can write as 0, 1. Okay, and you see you're generating all your standard unit vectors, okay, and you're going to add that to, you're going to keep adding that until you get to your last component, which you can write as that, okay. All right, and take note that these are all my unit standard vectors in S. So what is this? What is this actually? That is an element of. It's the element of the span of S. Okay, because V is a linear combination of the vectors in S. And what was the set S again? The set S was, well, I can go back, and this is my set S. Okay, it's the set of all these standard unit vectors. All right, next, what will be a spanning set of Pn? What would be a spanning set of Pn? Pn is all polynomials of degree less than or equal to n. So a spanning set there would be very similar to a spanning set of the previous set. So it's going to be all polynomials of the following form. So it's going to be 1x squared, carry on up until you get x to the power of n minus 1 xn. Okay, that's a spanning set. Why is that a spanning set? Okay, it's a spanning set because if you look at this polynomial, okay, take this polynomial. Let's take the general one. So you've got a0 plus a1x plus, carry on until you get to an xn. Okay. Now you can write that as a0 times my first polynomial in S, okay, plus a1, my second polynomial in S. You carry on up until an, and you get your last polynomial in S. All right, so now just go back to S. There's your S, okay? Now you can see that polynomial there is this one, that one is that one, the next one is going to be x2, and the last one, second last one, is going to be xn minus 1, and the last one is going to be xn. So what have I shown there? This is in fact what? This is in the span. It's in the span of S, because what's the span of S? The span of S is all the linear combinations of vectors in S, and this is S. So I've expressed P1 as a linear combination of vectors in S, and you can do this for any polynomial of degree less than or equal to n. All right, then the last one, what are the spanning sets of M22? M22 is the set of all 2 by 2 matrices. So I would probably say that a spanning set will look like this. So it's going to be all 2 by 2 matrices. Okay, you can take the second one as this. You can take the third one as this. And the last one you can take as, you're going to put a 1 there, you're going to put a 0 there, a 0 and a 0. Okay, so that is definitely, that's a spanning set of M22. And again, why is it a spanning set of M22? All right, why is it a spanning set of M22? So you can take any vector in M22. This is what it looks like. Okay, and you can write it as A times this vector plus B times this vector plus C times this vector and plus D times this vector. Now go back to your spanning set. There's my spanning set, okay? And this vector is that vector, that vector is that vector, that vector is that vector, that vector is that vector, and this vector is that vector there. So I've shown that, in fact, V is in the span of S. In other words, V is a linear combination of the vectors in S. So therefore, S is a spanning set, because I can express every vector in S as every vector in my set, V, I can express as a linear combination of vectors in S. Right, so they're asking me in this first example, given the vector W1 and the vector W2, they ask us to find the span of this set containing W1 and W2. All right, so how are we going to do this? Again, we apply the definition of span. So basically, the span of these two vectors is what? It's the set of all linear combinations of the two vectors. All right, and what's the K1 and the K2? The K1 and K2, these are real numbers. Okay, and now that we know what the vector W1 is, so it is pretty much just all vectors of okay, and that's the vector 1, minus 1, 2, 1 plus K2, 2 minus 1 minus 2. Okay, and that's where, remember, K1 and K2 are real numbers. Alright, so that is the span. It's the set of all linear combinations of vectors W1 and W2. Now, they'll ask us next, in B, they'll ask us, do these vectors span P2? Now, what is P2 again? It's the set of all polynomials of degree less than or equal to 2. So we want to know, do the vectors P1, P2, and P3 span P2? Now, for us to answer the question, we need to know what the definition of span is. The definition of spanning the span of a set of vectors is just the set of all linear combinations of that set of vectors. All right, so what we're going to do, with B, is we're going to let, so let's call this set S is P1, P2, and P3. Okay, so let S be that set. Now, does S span P2? So I'm claiming the following. I'm claiming that P2 is actually equal to the span of S. In other words, I'm saying that P2 span, I'm claiming that P2 is the span of S. So what am I saying? I'm saying that the vectors P1, P2, and P3, they span P2. Okay, now how do I prove that P2 spans S? How do I show that two sets are the same? How do I show that this set is equal to that set? I show it by showing that, firstly, I have to show that P2 is contained in the span of S, and I have to show that the span of S is contained in P2. So those are the two things I need to prove, to show that S spans P2. All right, so I want you guys to keep this in mind. I want you guys to keep that in mind. That's what I want to show. All right, now I can say the following, and I want you to answer me why this is the case. So, all right, so it is clear. So it is clear that that the span of S is contained in P2. All right, and that is true since P2 is a subspace, or P2 is a vector space. Okay, so any linear combination of vectors in P2 will be in P2. Okay, now what is the span of S? The span of S is all linear combinations of the vectors in S. Now, if you go and you look at any linear combination of these vectors, because P2 is closed under scalar multiplication and vector addition, it means any linear combination of vectors in S is also going to be in P2. So therefore, the span of S is contained in P2. Right, now we need to show the, so we know span of S is contained in P2. All right, now, okay, so if we go back to that thing we need to prove, so we've proven this part here, and now we need to prove that part there. Okay, how do we prove that? By taking a point in P2 and then showing that it is in the span of S. How do we show it's in the span of S? What needs to happen for something to be in the span of S? It needs to be a linear combination of vectors in S. So I need to show that every vector in P2 is a linear combination of vectors in S. All right, so that's what I'm going to do. I'm going to take a polynomial from P2. All right, what does a polynomial from P2 look like? It looks like this. Okay, that's a polynomial in P2. All right, that's in P2. And now what I'm going to do is I'm going to now prove that this polynomial is in fact in the span of S. Okay, so, right, so how do I do this? All right, so what I'm going to do is I'm going to let K1, K2, and K3 be scalars. Okay, such that let's see if we can express the polynomial a0, a1x plus a2 x squared as a linear combination of the vectors p1 plus k2 p2 plus k3 p3. All right, so that means that our function is k1 p. What's p1? P1 is the polynomial 1 plus k2. What is p2? Okay, that is 1 plus x minus x squared. Okay, right, plus k3, 1 plus 2x squared. Okay. Right, now what we're going to do is gather the like terms on the left, the x's and the x squareds, and we get the following. Okay, so that gives us a polynomial that's equal to 0 for all values of x. And this is true for all x. So it has to be true for all x, so it doesn't matter what I make x. This polynomial must be 0. So what do we know about how many roots can a polynomial of degree 2 have? It can have at most 2 roots. Now, if this expression is not 0, then we've got a polynomial on the left-hand side that is degree 2, and it's equal to 0 for all values of x, meaning that this polynomial is going to have infinitely many roots. And can that be possible? No. So this underlined red, that has to be 0. Okay? If this is not 0, then we've got a polynomial of degree 1 on the left-hand side, equal to 0 for all values of x. And this is going to mean that if I plug in any value of x in there, I'm going to get a root. And a polynomial of degree 1 can have at most 1 root. It cannot have infinitely many roots. So this thing here needs to be 0. Right. Now, if this is not 0, then we've got a polynomial on the left-hand side, which is not 0. And on the right-hand side, we've got a 0 term, and that's impossible. So this thing has to be 0 as well. All right, so that implies, first of all, that a1 minus k2 is 0, which we know is going to imply that k2 is equal to a1. We have that a2 plus k2 minus 2k3 is equal to 0, which implies that k3 is equal to a half a2 plus k2, which in this case is a1. And we also have that a0 minus k1 minus k2 minus k3 is equal to 0, which is going to imply we haven't solved for k1. So k1 is going to be a0 minus k2 plus k3 and we know that K2, what is K2? It's A1. And we know what K3 is. It's going to be a half. A2 plus A1. All right, so clearly we've solved for K1 as a valid real number. We've solved for K2 as a valid real number, and we solved for K3 as a valid real number. So what is the answer to the question? It means that can we write a vector in P2 as a linear combination of vectors in S? Yes. Okay, so it is clear. It is clear that A0 plus A1x plus A2x squared is in the span of S, which will imply that P2 is equal to the span of S, because I've shown that any chosen vector in P2 is a linear combination of vectors in S. All right, the next statement is a spanning set for a vector space is not unique. Now what that means is you could get two or more different sets that span the same vector space. So it's not true that you're always going to get only one spanning set for a vector space. You could get many different spanning sets. We'll see later on in section 4.3 and 4.4 where there are examples of more than one spanning set. Okay, so Theorem 4 states that if S and S prime are non-empty subsets of a vector space V, then the only way that the span of the two sets are equal, that only happens is if every vector in S is a linear combination of vectors in S prime, and each vector in S prime is a linear combination of the vectors in S. Right, so let's just look a little bit deeper into this. Let us assume that, firstly, that the span of that vector set is the same as the span of that vector set. Why does it then imply that every vector in S is a linear combination of vectors in S prime and vice versa? Well, the reason is that if these two things are equal, then let's take the vector V1 as an example. Now V1 is in the span of the set S, right? Because V1 is a linear combination of itself. So you can write V1 as 1 times V1 plus 0 times V2 plus up until I can write that down. For example, you can write. Let's just look at this. So you can write V1 as 1 times V1 plus 0 times V2 plus up until the end 0 times VR. So you've expressed V1 as a linear combination of vectors in S. Okay, so V1 is in the span of S, and because these two sets are the same, and because V1 is in the span of S, V1 is also going to be in that set there. And for V1 to be in that set, it means V1 must evidently be a linear combination of the vectors in S prime. So therefore, every vector in S is a linear combination of the vectors in S prime, and vice versa. If you take if you take the vector, let's take the vector W1, and let's W1 is clearly in the span of S prime, because you can write W1 as a linear combination of vectors in S prime. So you can write W1 as 1 times W1 plus 0 times W2 up until the end. Okay, 0 times WK. Alright, so W1 is a linear combination of vectors in S prime, so it is in the span of S prime. And because the span of S prime is equal to the span of S, W1 is in the span of S, and therefore W1 is a linear combination of all the vectors in the span, all the vectors in S. Okay. Right, so I just quickly want you guys to visualize this. Why is it that if every vector in S is a linear combination, if every vector in the span of S, or rather if every vector in S is a linear combination of vectors in S prime, and every vector in S prime is a linear combination of vectors in S, why does it mean the span of S is equal to the span of S prime? Well, just visualize it. I'm not going to write it out, but let's say every vector V is a linear combination of vectors in W in S prime. So now remember, you can write you write V1 as a sum of scalar multiples of vectors in S prime, and you can write the ith vector in S as a linear combination of vectors in S prime. Now take this vector here from the span of S. Okay, so it's a vector in the span of S. Now we want to show that this vector is in the span of S prime. How do we do that? Well, we can take this V and we can plug it in there, and we're going to get only W terms. Then we take the we make I2 and we plug that term in there. Then we make I3 and we plug it in there. And in general, we can do it for the last term. We plug that, if we make IR, we plug that whole expression there, we plug it in there. And what happens if you gather all the like terms, all the W1 terms, all the W2 terms, and up until all the WK terms? If you group them all together, you're going to get a linear combination of vectors in S prime, which is then a vector in but pretty much the span of S prime. So one can easily see that this vector, doing a substitution, that vector will be also in the span of S prime. And you can do the same argument. You can take a vector in S prime and show, you can take a vector in S prime and assume that it is a linear combination of vectors in S, and then again you can do the same substitution, and you can prove that the span of S prime is in fact contained in the span of S. So that's why those two, the spans are the same. If every vector in S is a linear combination of vectors in S prime, and vice versa, then the spans of S is going to be equal to the span of S prime. And it follows from it follows from that substitution that I make. All right, the last theorem, Theorem 5, says that the solution set of a homogeneous linear system, AX equals 0, in n unknowns is a subspace of Rn, and it's called the solution space of the system. Now Rn, we know what the vectors in Rn look like. It's all n tuples where the each component is a real number. So the solution space happens to be a subspace of Rn. Now why is the solution space a subspace of Rn? How do we prove this? we need to prove that for the solution space is closed under vector addition, and we need to show that the solution space is closed under scalar multiplication. All right, and that's not that's not difficult to do. All right, so right, so we can take let x and y be in the solution space. Solution space S, let's call it S, of the homogeneous linear system. Okay, now if you take the sum between the two vectors, right, that is going to be ax bar plus a y bar, and x is in the solution space, so ax bar is going to be the 0 vector and y is in the solution space, so that's going to be the 0 vector and that's the 0 vector, and so that implies that x plus y is going to be in the solution space, right? And what happens with scalar multiplication? Right, so we can take a scalar. It can be a real number. Then if you take k multiple of x, right, we know from vector multiplication, what's that going to be? That's going to be the scalar ax bar. We know x bar is in the solution space, so that's going to be k times the 0 vector, which is going to be the 0 vector. Okay, so what is the moral of the story here? Is the solution space closed under scalar multiplication? So that implies that k bar is in the solution space. Alright, so hence S is a subspace. Subspace of Rn. Alright, so here they ask us find the solution spaces of the following systems. Okay, I'm going to leave the second and the third one for you guys as an exercise. I'm going to look at the first one. So, I mean, this is already work that we've done. What is the solution space of this homogeneous linear system? So it's got that 1, 2. It's got 0, 0, 0, and then it's got the vector. Let's call that x. And that is the 0 vector. Okay. Right, so that implies then that x minus 2y plus 2z is equal to 0, and basically y plus 2z is equal to 0. Okay, and that's my first equation, and that's my second equation. So then we can, what we can do is we can take 1 and subtract 2 from that. So we get that x minus 2y plus 2z minus y minus 2z is equal to 0. And from that, so the z's cancel one another out, and you basically left with x minus 3y is equal to 0, and that implies that that y is equal to a third x. Okay, and so from 2, we can solve for z as minus a half y, and so z is minus a half. What is y? It's a third x. Okay, so that is minus 1 over 6x. Okay, so what is the solution space? The solution space is basically, it's all vectors of the form. So we can parameterize, we can let x be t, then we can solve y as a third t, and we can solve z as minus 1 over 6t. Alright, and what is t? T is a real number. Okay, so that's my solution space. It's all vectors of that form.